In this video, we will solve the Schrodinger equation for the two-dimensional rotation by converting the xy Cartesian coordinates to the r theta polar coordinates. So over here, this particle is rotating about the center of a ring with a constant radius r0. This is the x-axis. This is the y-axis. So the Cartesian coordinates of this particle x is equal to r0 times cosine theta, y equals r0 times sine theta. And then we write out the time-independent Schrodinger equation here, which is the kinetic energy in the x direction plus the kinetic energy in the y direction being applied to the wave function of the particle. We get E psi. What about the potential energy? It's a free rotation, therefore the potential energy of the particle is 0 as long as the particle stays on this ring with a constant radius of r0. And then again we have x equals r0 cosine theta, y equals r0 times sine theta, and tangent theta equals y over x. We will then convert this Schrodinger equation to polar coordinates. We'll have to use the chain rule for the transformation. First, let's look at the first derivative of psi with respect to x. So the chain rule tells us this delta psi over delta x equals delta psi over delta theta times delta psi over delta x plus delta psi over delta r times delta r divided by delta x. Why is that? Psi changes with x, and x is a function of r and theta. So over here, the physical meaning is if we change x, theta will change. When theta changes, psi changes. When x changes, r will change. When r changes, psi will change. Therefore, when x changes, psi changes with two intermediate variables, r and theta, being changed. But in this case, we're fortunate. This r is a constant. We don't have to worry about the second term. So essentially, it's just this. Psi changes with theta, and theta changes with x. This is the chain rule. So we just have this simpler term. And how about delta theta over delta x? It's a little bit difficult to do. We'll have to introduce another intermediate variable, the tangent theta. Well, this term is equal to delta tangent theta over delta x times, again over here we'll have to kind of cancel this tangent theta, so it's here. And then we can do this because this thing, the first derivative of tangent theta is simply 1 over cosine theta squared. And over here, this tangent theta can be rewritten as y over x here. Remember here? So it's just the first derivative of y over x. And that can be easily done. It's negative y over x squared. And then we keep this term here. So we simplify this by replacing y with r0 times sine theta, and x is r0 times cosine theta. In the end, we simplified the expression of the first derivative of psi with respect to theta. So it's over here. And then we evaluate the second derivative of this guy. So we do the first derivative of psi with respect to y here. We get a similar result. Now the second derivative. The second derivative is actually easy. Well, although tedious. So we need to just apply this first derivative operator twice. So over here, this is our first derivative. So we just need to apply this negative sine theta over r0 and delta over delta theta twice to this side. So that's what we do here. Negative sine theta over r0 and delta over delta theta. That's the first derivative operator, and then another first derivative operator here. So we apply the first derivative operator twice to the side. So I'm going to skip all those steps and show you the result. It looks complicated. It's right here. And then similarly, we do y. When we do y, we get a similar result over here. So actually, you can get the second derivative of psi with respect to y easily by replacing over here. If you see any sine theta, just change it to cosine theta. When you see cosine theta, change it to negative sine theta. So if you do that, sine theta times cosine theta becomes cosine theta times negative sine theta. So we got a negative sign here. And then we replace sine theta with cosine theta. So this guy is this guy. And then we need to sum up this term and this term. Remember, the kinetic energy operator consists of the x direction and the y direction. So we sum this and this. Fortunately, this part and this part, they cancel. And this part and this part, you see sine theta squared plus cosine theta squared, which is just 1. So in the end, if you sum it up, this 2 equals simply the second derivative of psi with respect to theta divided by r naught squared. And then the Schrodinger equation is simplified to this. And I is the moment of inertia. How do we solve this? It's very simple. The solution is just the normalization factor times e to the power of I times m sub L times theta. What is m sub L? We define m sub L to be the square root of 2ie over h bar. The physical meaning of the square root of 2ie is simply 2 times this m r naught squared times 1/2 times m times r naught v squared. So this v, this e, is simply the kinetic energy of the particle because the potential energy is 0. If we combine this 2ie and then take the square root, this is actually the angular momentum of the particle. So m sub L is the angular momentum divided by h bar. H bar is actually equal to 1 in the atomic units in quantum mechanics. All right, the boundary condition. So in this free rotation problem, because of the periodicity, we have psi of theta equals psi of theta plus 2 pi. So again, this theta and theta plus 2 pi give you the same position of the particle. Therefore, we have this equation because the wave function must be single valued. And then using this periodicity or boundary condition, we see that m sub L will have to be an integer. M sub L can be 0 or negative integers or positive integers. So we set m sub L to be plus minus L, and L is non-negative integer. L equals 0, 1, 2, 3. When m sub L equals 0, it tells us the psi is simply a constant. And to normalize this psi, this normalization constant has to be 2 pi r naught to the power of negative 1/2. Remember, the integral of psi squared over the entire circular space is 1. So this guy squared is 1 pi r naught to the power of negative 1, and we integrate this constant over the entire space, which is 2 pi r naught, and then you have actually 2 pi r naught divided by 2 pi r naught, you get 100%. The physical meaning is the probability of finding the particle on the ring with a constant radius r naught is 100%. All right. Oh, by the way, this m sub L and L can be found in any general chemistry textbooks. In those textbooks, L is the quantum number for the 3-dimensional rotation, and m sub L is the z component of L. But in here, we're looking at just the 2-dimensional rotation. All right, for a 2-particle 2-dimensional rigid rotor, so this means R naught doesn't change, such as HCl. We're assuming this distance between HCl doesn't change, okay? And then, although both H and Cl move, both H and Cl rotate, the center of mass of HCl doesn't. So basically, H and Cl are both rotating about the center of the mass. And the center of the mass is very close to the position of chlorine because chlorine is heavier. Therefore, the motion of the chlorine is less prominent than the motion of hydrogen. And then the Schrodinger equation can be written as follows. The only difference here is the mass of one particle should be replaced by the reduced mass of 2 particles. And how do we compute this mu, the reduced mass? 1 over mu equals 1 over m1 plus 1 over m2. Basically, if you have 2 particles, you just plug in the mass of particle 1 here and the mass of particle 2 here. And what about the rotational energy? Again, it's m sub L squared times h squared over 2I. Again, this can be 0. When m sub L equals 0, this is 0, and it's fine. The wave function is non-zero. The wave function is simply this 2 pi r naught to the power of negative 1/2. Again, this I is the moment of inertia of the two-particle rotor. The mu is the reduced mass, r naught is the distance between the two particles. Again, this m sub L can be plus minus L. Well, this L is a non-integer. L is a non-negative integer, 0, 1, 2, and so forth.